unit circle is all based around symmetry. If you know the two special triangles that we talked about in our last lesson, then you will always be able to identify the coordinates of not all key points on the unit circle, but all the major ones that we are going to use. Okay, so at 30 degrees, right, the cosine of 30 gives us the coordinate square root 3 over 2, and the y coordinate is the sine of 30 degrees, which is 1 over 2, right? And I'm basing this off the special triangles that are on the board. 1, 1, root 2, 45 degrees. 1, 2, root 3. This is 30 degrees. This is 60 degrees, right? So the cosine is adjacent over hypotenuse, and the sine is opposite over hypotenuse. That's how I got those numbers, right? And we're going to do that for all of the angles all the way around. At least that's what I want you to think. Okay, for the 45 degree, the sine of 45 is 1 over root 2, and the cosine is also 1 over root 2. However, when we are dealing with trig, I do want us to be rationalizing the denominator. So really this is 2 root 2 over 2. Right, root 2 over 2, root 2 over 2. This will make our life easier later on down the road. Okay, and then at 60 degrees, again, looking at our special triangles, this is going to be 1 over 2 for the cosine and root 3 over 2 for the sine. Now, I'm not going to keep doing this over and over again. I'm going to use the idea of symmetry. Okay, for 30 degrees, I can use it as a reference angle. When I go to quadrant number 2, you'll notice that I have identified where the 30-degree angle is. It's at 120, right? 180 minus 120 is 30 degrees. So the coordinates at 150 is going to be root 3 over 2 and 1 over 2. The only thing I have to worry about is what is positive and what is negative, right? Because in my first quadrant, everything is positive. In my second quadrant, only sine is positive. Sine represents the y value. So sine is positive. That means this is negative root 3 over 2. Okay? And I follow the symmetry. All of these coordinates end up being exactly the same as before. Negative root 2 over 2. Positive root 2 over 2. Negative 1/2. Positive root 3 over 2. Okay, and again, because of symmetry, because of what we call the bow tie method, right? Look for where are these things the same. Here is 30 degrees. Here is reference 30 degrees, and I can keep going underneath as well. Here is my reference 30 degrees. Here is my reference 30 degrees. So I'm going to use those same coordinates in all the other quadrants, but now different things are positive and negative. Okay, so this is 30 degrees. So 180 plus 30 gives me 210. 180 plus 45 gives me 225. 180 plus 60 gives me 240. So I'm matching all the pink coordinates, green coordinates, blue coordinates, all the way around the circle. In quadrant 3, only tangent is positive, so both my numbers in this case are negative. Right? Cosine is x, sine is y, positive, negative. Okay, so I'm going to let you finish this one up on your own. I will post the final full unit circle later on. But key ideas I want you to understand. The horizontal line is our x-axis. Okay. This means the y's are positive when we go up, and the y's are negative when we go down. So that means sine is always positive in quadrants 1 and 2. Sine is always negative in quadrants 3 and 4. Likewise, this is the y-axis. All right. If this is the y-axis, that means all x values to the right are positive and all x values to the left are negative. That means cosine is always positive in quadrants 2 and 3. Sorry, cosine is negative in quadrants 2 and 3 because cosine is our x values, and positive in quadrants 1 and 4. Okay, but if you know how to get these basic angles, what are the coordinates? 0 starts at 1. 90 degrees ends at x is 0, y is 1. And what are the 3 key angles in between? You will know all the coordinates all the way around the unit circle. Okay? So this is a bit of a review from yesterday. Today, what we're going to focus on is essentially the same thing, but we are going to change units. Rather than measuring our circle in degrees, we are going to measure them in something called radians. Okay, so let's flip over to lesson 2 in our books. Okay, so the radian measure, the units for radians are identified as rads. Hopefully that's easy to remember. Radians is rads. And they come from the equation of the circumference of the circle. Remember that the circumference of the circle has the formula C equals 2 pi r. Some of you will have learned this differently as pi times d. D is the diameter, which is 2 times r, right? Radius is halfway across the circle, diameter is all the way across. So we can write the circumference of a circle either as pi d or 2 pi r. Now, when we're focused on the unit circle, we know that our radius is going to be 1. So when we substitute 1 is r, we get that the circumference of the circle can be simplified to 2 pi. And so that's kind of where the pi pieces, I guess, come from. Before, we said we're going to start at this point. The coordinate for this point is, 1, 0. X is 1, y is 0. So we're on the x-axis starting at the point here. We say that this is 0 degrees. And if we go all the way around the circle, then this is 360 degrees. We are now translating that into radians. Now this is 0 radians. And if we go all the way around the circle, meaning we are covering the circumference of the circle, all the way around a circle is 2 pi rads. Okay, so we start at 0 and end at 2 pi. What happens if I go halfway across the circle? How many pi's is this? 1 pi, yeah. This is pi. So pi is equal to how many degrees? What's half a circle? 180 degrees. Okay, what if I go a quarter of the way? What if I stop up here? 90 degrees represents how many pi's? Half a pi, yeah, pi by 2. Okay, and if I go 3/4 of the way, pi plus half a pi, how many pi's is this? 1.5. Can we reduce that to 1 fraction or put it together? 1.5 is what as a fraction? 3 halves, yeah, 3 pi over 2. Okay, so these are our new measurements. We are measuring the circle in pieces of pi. This is going to be super helpful for us. 180 degrees is represented by one, you can think of it as a slice of pie. So what we want to do is we want to figure out how can we convert any degrees or any radians between the two different kinds of measurements. And what we're going to use is equivalent fractions. Because this is true, that means I can set this up like this. I can say pi is 180 degrees, which means I can set up any fraction with rads on top and degrees on the bottom. And then I can use cross multiply and divide in order to find any form of degrees or any form of radians, because I know that the ratio of pi and 180 is true. So let's think of 30 degrees. If I know that my degrees is 30, then I can use pi over 180 equals, and I can use a variable here. Maybe I'm going to use the variable theta. How many radians is my angle if I know that my degrees is 30? Right? So I have to match up. Degrees go with degrees and radians go with radians. Use the symbol theta to put the unknown, what you don't know. Okay, if I were to rearrange this equation, this would give me theta is 30 times pi over 180. How many pieces of pi is this? What fraction of pi is this? Reduce the fraction for me. 30 over 180. 1 over 6 or pi over 6. Right? So this is the same as 30 degrees. So somewhere over here, where this is supposedly 30 degrees, this is now going to be pi by 6, a sixth of the pi. And we're going to do the same thing for all of our different angles. Okay. Pi over 180 equals theta over 45 degrees. Theta equals what? Reduce the fraction. 45 over 180. How many radians? Pi by 4. Okay, that's my next angle. So 45 degrees is the same as pi by 4. Okay, and our last one is pi by 180 equals theta over, what's my next angle? 60 degrees. Pi by 3. Okay, so now I have rewritten my unit circle. I've done nothing new. I've just changed the measurements. Okay, all of the things now remain true. So we can actually redraw. Maybe I'll just do it at the bottom of my, or kind of in this spot here. I'm going to redraw my special triangles. Okay, 1, 1, root 2. And instead of writing 45 degrees, I'm going to now say this special triangle is related to pi by 4. The coordinates stay the same. I'm just changing my units. Right? Same with this one here. 1, 2, root 3, 90 degrees. The big angle, pi by 3, right? A third of the pi is bigger than a sixth of the pi. Remember, 30 degrees and 60 degrees, pi by 6, pi by 3. Okay, so we can still do the unit circle now with our new measures, and we can still use these measures as our reference angle. Okay, so here is an example of a conversion. We already know that 30 degrees is pi by 6. We just did it up top on our page. Let's go backwards. Here I have radians, and I want degrees. I'm going to use this as my setup for the formula, right? I'm going to say pi by 180 equals, now I know my radians, 7 pi by 4 over, I don't know my degrees now, so I'm going to put my theta in place of the degrees. Okay, when we have equivalent fractions where the unknown is in the bottom, how do we solve? Inverse, yes. There's like a nice little saying that we use. You're not wrong. The method that you're saying is correct. Any ideas? Yes, and cross multiply and divide, yes. So anytime you have equivalent fractions with an unknown, especially if the unknown is in the bottom, start at the top of the fraction, cross multiply, and then divide. Okay, so theta is going to equal 7 pi by 4 times 180 divided by pi. And you can chuck this in a calculator, or you can do it in your head. Yes, 350 degrees. Please do not forget your units. Because we are switching back and forth, it's going to be really important to keep your units straight. Any questions about this? Comments, concerns? Okay. Let's look at another set of ratios. Here I have a complete circle. When we cut a circle into pieces, what we are trying to do is solve for certain parts that are unknown to us. And the way that we're going to solve this is by recognizing that a part of the circle and its ratio to the whole is going to be equivalent to whether we're measuring the angle, a length, or the area. The piece compared to the whole is going to give us the same ratio whether it is area, circumference, or angle. Okay, so let's do a little visual example of what I'm talking about. Draw a little dot in the middle of your circle and draw the radius somewhere. And then draw a radius somewhere else, like you're cutting a piece of the circle, like a piece of pie or a pizza. So start in the middle and just cut a piece out. Okay? Now, the angle, which we're going to represent with theta, the radius, which we're going to represent with r, and the arc length. Arc length means the length around just the piece that you cut out. That is your A. Okay, so arc length equals A. The length of the piece, but just on the outside. Okay, what this is saying is the ratio of A compared to the circumference, right? Circumference is the entire pie, C, right? So the piece A compared to the whole thing C is going to be the same as the piece of the angle theta compared to the entire angle of the inside, right? The entire circle is 2 pi radians. So the piece compared to the whole is the same. And it also applies to area, right? If I were to color in this piece, the area of the piece compared to the area of the entire circle, A, is going to be the same. So we can use this. We will always know some piece of information that will allow us to solve for all and other missing pieces. Okay, so let's take a look. Find the arc length. What do I have? I am told, let's call this R. I know that my radius is 10 centimeters and my angle right here is 1.7 radians or rads. Sometimes radians are pieces of pi and sometimes they're just decimals because you just put the pi into your calculator. Okay. Radians. I'm looking for arc length, so I'm going to use these two. This is going to be my equivalent fraction. I know theta, I know r, I know 2 pi. The thing that I'm missing is a, and that's what I want. So if I write my equation, a over 2 pi r equals theta over 2 pi, you'll notice something right away. Both of them have a 2 pi in the denominator. Let's just simplify. They're both in the denominator, therefore I can just cross them off. Right? Because the way that I'm going to solve for a is I'm going to have to multiply both sides, by 2 pi, and they're going to end up going away anyway. So let's just simplify. This means that a over r equals theta. This simplified version is still true for all circles, regardless of the size. Well, I know r and I know theta. So for this question, a equals 1.7. That's my radians. I'm going to have to multiply by r, right, to get r to the other side. So multiplied by 10. What's my arc length? 17. 17 what? Centimeters, right? Because it's a length. So the length of that little chunk of pi is 17 centimeters. Okay, in example B, find the sector angle. So now I'm looking for theta, and I start with this equation, right? Because it's true for all circles. A over r equals theta. My r is 4, and my arc length is 6. So 6 over 4 equals theta. And if I'm going to reduce this, right, we always reduce our fractions. Theta is going to be 3 over 2, what? Not centimeters. Radians, so it's 3 over 4 rads. Or you could say 1.5 rads. That's fine too. If you leave it in fraction, make sure it's reduced and rationalized. Or write it as a decimal. Either way is fine. Okay, and lastly here, find the radius. We are told that the angle is 30 degrees and that the arc length is 12 centimeters. Now, because we are working with ratios in radians, we must use radians. Okay, so pi over 180 equals theta over 30. Theta is pi by 6. We did this part on the previous page, right? So make sure your theta is in radians first. So now I know my theta is in radians pi by 6, and I know that my A is 12. A over R equals theta. So that means A over theta equals R. 12 divided by pi by 6. How do we divide fractions? What's the rule? Flip and multiply. Yes, so we need the reciprocal. So this is 12 times 6 over pi. So again, two ways you can write it. 72 over pi, or you can check it into your calculator. It'll give you approximately 22.9, and this would be in centimeters. Okay, so the focus of our lesson today is understanding the relationship between degrees and radians, making sure we can convert, and making sure that we can find the arc length. So before the end of today, what I would like you to do is go back to your unit circle. And once you have everything filled in for degrees, go ahead and add in your radians. So 0 is 0. 30 degrees is pi by 6. Pi by 4. Pi by 3. So go all the way around your circle. Make sure you have the degrees filled in. Make sure you have the radians filled in. And the rest of time you have to work on your homework.